Hello, my name is Darren Thomas, and I am the Director of Educational Research Techniques. In this video, we're going to take a look at the sinusoidal function and the ideal of phase shift. So let's go ahead and get started. So if you look here in the upper corner of the screen here, you can see this is a picture of a sine function. Now I need to also mention that everything I'm talking about here also applies for cosine. We've just been using sine for simplicity's sake because it's just the first one we talk about often. And so you can see here that, we clearly here have an amplitude of 1. We have a period of a 2 pi, if you will. And these are all the basic characteristics. It's centered, everything is, 0. But to try to clarify what I'm talking about, I'm kind of talking about this. So to clarify what I'm talking about, I'm essentially talking about this. So you got your y equals a sine b times x minus c plus d. This is kind of the standard one. And so the a is the amplitude. We've talked about that in prior videos. So this is the amplitude. Just call it amp for short. B, this is used to figure out the period. B by itself is not the period. I'm sure you remember that. But it's used to figure out the period. C is for determining whether it's going to the left or to the right. This is the phase shift. That's kind of the focus of this video. And the D has to do with the vertical, how up or down it is on the y-axis. So this is kind of what we're looking at in this video. Is we're focusing really heavily on this guy right here, figuring out how far to the left, to the right the function is, basically compared to the regular sine function, in other words. So shift to the left, shift to the right, what's going on there, and the characteristics behind that. So there's one other way to write this, and this is also going to be used primarily for when you're trying to deal with the phase shift, if you will, and that is y equals a sine, then you have b times the quantity of x minus c over b. It was a little crooked there, but you get the point, times, plus d. This is just, now the thing is, if you distribute the b again, or if you distribute it, you'll get bx again, and then of course b over 1 time that you'll get bc, and then you'll get c again. So basically all you're doing here is you're using one of the properties of algebra here, while you put the b out here. But if you distribute this b, you're going to get the original equation. So there's really nothing radical going on here. However, the key point that's going to make sense in a second is that by doing c over b, you can figure out what the phase shift is. That's kind of the point. So of course the original equation is much more efficient. I mean, it just makes more sense in many ways. But this particular rewriting of it is useful for trying to figure out the phase shift. And so let me just give you some examples and stop talking theoretically here. So the black line here is, of course, our original sine function where nothing has moved. So c is set to 0, d is set to 0, b is set to 1, the a is set to 1, etc., etc. The red is going to be when we have a phase shift here. And so you can see that in comparison to the regular sine function, this red line is moved to the right. And so let me go ahead and write for you the equation for this guy's behavior. So it's sine, it's sine. The equation is sine. So the equation, like I was trying to explain a second ago, is going to be sine. Oh, that's not the color I want. Sine. And then we have x minus 1. And just to complete the thought, boy, I'm really crooked today here. Let me straighten this up. X minus 1. And just to complete the thought, we're going to put 0 here. So what's happening is this. B in this particular situation is set to 1. So I should make this a 1x. I guess, if I had to be technical about it. Let me start with the A. The A is essentially set to 1. So A is equal to 1. So our amplitude is 1. B technically is set to 1 as well. C is set to minus 1. And D is set to 0. We're just trying to complete the thought here. You don't normally put the 1s and the 0s here, as you can see, but we're learning here. Now, here's the thing. To figure out what the phase shift is, although you can see it here in the screen, to figure this out, you do the following. you take C and then you put it over B. That's what you do. So in our situation, it's going to be negative 1 over 1, which means that our phase shift is minus 1. Now, you can see here, if you're looking closely at the screen, that yes, you can see that our wave, our sinusoidal function here, it moved to the right by 1. So this is the first important point that we need to understand. If your phase shift, if the answer is a negative number, that means that you're going to go to the right. If it is a positive number, that means you're going to go to the left, like so. And so let me demonstrate that in the next example. All right, so you can see here the blue line here is, of course, the modified sine function compared to the black line, which is again our standard one. And so it's basically, there's not a whole lot new here. It's just that now we have sine of x plus 1, minus 0. I can put the ones here to kind of complete the thought. And so the only difference between this one and the last one is that this time our c is a positive number. So again, if I go through all the steps here and I do c over b like before, I got 1 over 1 equals 1. This is obviously a positive number, which means this time we're going to go to the left. Like I showed you in the last slide, we're going to go to the left one. And you can clearly see that compared to the regular sine function, this one has moved to the left 1. And so now it's lined up at negative 1 here. That's kind of what's happening there. So again, not that deep. But let me give you one more example, something that's a little bit more complicated. So this is quite the monster here. Remember, the black line is the original sine function, and now this time the green line is some crazy function. So what exactly is going on here? All right, let's take a look at it. Let me tell you what the equation is. So our equation in this particular example is 2 sine times the quantity of 2x plus 2, and then still minus 0. So this time our a is 2, our b is 2, our c is 2, and for right now our d is 0, because we're going to learn about d in the next video. All right, now what is happening here? So we've been focused primarily on trying to figure out what the phase shift is. So we'll deal with that first, because that's what we're dealing with. So c in this particular instance is, c is 2, b is 2, so our phase shift is a positive 1, supposedly. And so you can see that compared to this, so when it's positive, remember that when it's positive, it goes to the left. So you can see here that, it's right here at 1, starting at negative 1. It went to the left 1. Okay, so we know what the phase shift is 1. But why is it wider and smaller? Well, these are review ideas that we talked about in previous videos. So you can see here that the period is much higher. The period for the black line is 1, but this one goes up to 2. And remember, the period, in case you forgot, is going to be 2 pi over b, which in our case, 2 pi over 2 was equals pi. Now, when the b value is greater than 1, it compresses things. It stretches things. Yeah, it stretches things. So you can see here how it stretches up to 2. I'm sorry, what am I talking about? This is the, wait. Hold on. So let me clarify myself here. What's happening is that the period is about the horizontal space. And so you can see here that because the value is greater than 1, the b value, it compresses things a little bit. And so you can see that there's more frequency of the green line compared to the black line, if you will, in terms of like the number of peaks and valleys or whatever. And that has to do with the period. Sorry about that confusion there. Now, we're going to deal with the amplitude, and the amplitude is basically the distance here from top to bottom, if you will. And so to get the amplitude, you do 1/2. This is amplitude, by the way. 1/2 times the quantity, times the absolute value of the maximum from the minimum, subtract from the minimum, like so. Now, so 2 minus negative 2 is going to be 4, and then 1/2 times 4 is going to give us an amplitude of 2. And you can clearly see this on the graph that the amplitude goes up to 2, down to -2, and so it's stretched compared to what we normally expect. So the amplitude is stretched here, however, the period is compressed, and that's why this looks different. And then we still had that phase shift to the left by 1. So we made it a little bit more complicated here, but trying to tie together the different ideas we've talked about over the past few videos. So let me go back and review and we'll wrap this up. So in this video, we got introduced to the ideal of the phase shift. And so the phase shift for us is trying to measure how the function moves to the left or to the right. It's talking about the horizontal moving back and forth in comparison to the regular sine function. And so we talked about the equation right here. You're really focused on that c term and how it behaves. And then we went through a few examples here. In this particular example, the phase shift was a negative number. When it's negative, the function moves to the right. When it's positive, the function moves to the left, as we already mentioned. And so then here's our example of it when it's a positive number, as mentioned before. And this one we got a little bit more complicated. I tried to keep it clear. I know I made quite a mess. But in this one, we have multiple different values for our A, B, and C terms. But we haven't dealt with the D term yet. And so what happened was that the period was compressed because the B was greater than 1. And so you can see how the period is closer together compared to the regular sine function. And then with the amplitude, it was stretched because of the behavior of the function. So you can see that it was stretched because it was greater than 1, I believe, in this particular example. So the amplitude was 2 instead of 1. So I hope this was useful for you and that things made sense here. My name is Darren Thomas. I am the Director of Educational Research Techniques. Take care.